Let's now take a look at a few Python examples for z-transform, and we will start with the z-transform of an exponentially decaying function defined like this. So we have our signal 0.5 to the power of n for n greater or equal to 0 and 0 elsewhere. When we apply the z-transform, we will get this summation here, and this summation is equal to this here. So here we can see a pole when z is equal to 0.5. We can see that the z-transform converges for all values when the absolute value of z is greater than 0.5, and this is called the region of convergency. And we can see there is a correspondence of an exponential time function to a pole in the z domain. So by looking at the z-transform here, we can see that there is a correspondence of an exponential time function and a pole in z domain. So let's see how did we solve this, how do we go from here to here, and let's make use of the geometric sum. So the geometric sum is a summation like this. So let's use a trick. So if we multiply this here by a, so we will have a times s. So a will go inside here, and there will be a summation with a to the power of n plus 1, and this is the same as if we do the summation from n equals to 1 until n, capital N plus 1. So this is the original geometric sum. We multiply this by a, and we will obtain this. So now we will take a times s, which is this, minus s, which is this. So a times s minus s is the same as s times a minus 1. So a times s minus s. And we will have that a times s we had here, and s we have here. So when we take this summation minus this summation, we will end up with a to the power of n, capital N plus 1 minus 1. So if we expand the sum, we will see that all the elements will cancel, because we're taking one minus the other and they will be equal, not for the last element of this sum, which is a to the power of n when n is equal to n plus 1, and here we will have when n is equal to 0. So we have here a to the power of 0, which is this one here. So when we take a times s, this summation, minus s, this summation, we will end up with these two elements here. So if we now divide these elements by a minus 1, we will get that this summation is equal to this divided by this. With some manipulation, we end up like this. So if we multiply up and down by minus 1, we have here. Now, if we replace this a by the z-transform here, so this is a summation if all of this is equal to a to the power of n from 0 to infinity. So that's what we're doing here. We're replacing this a here by this, and we get this here. But now we don't want from 0 to n, we want from 0 to infinity. So if we take the limit when n goes to infinity, this factor here will go to 0, and we will end up with this result here, 1 over 1 minus 0.5 times z to the power of minus 1, which is what we've seen here. So we use the geometric sum and this trick here of multiplying by a and then take a times s minus s. So when we do this summation minus this summation, only what is left is this factor here minus this when n is equal to 0 here, and we have our result. We can also use SymPy to solve this. So if we don't want to do all these maths, we can make use of symbolic pi. So we're importing symbolic pi. We're defining the symbols, and here we're doing summation 0.5 times z to the power of minus 1 here to the power of n, here going from 0 to n. So there it is. We have here the same result as here. So it's 1 minus 0.5 times z to the power of minus 1 to the power of n plus 1, what we have here, and this here is here. So when if we would do the limit when n goes to infinity, this here goes to 0, and we end up with here. Unfortunately, SymPy has some limitations, and especially when we are dealing with infinity, and it cannot calculate the infinity in this case. So for example, if I change here to infinity, we will have an error. So it just gives me which is the exactly this here. So it cannot calculate, or if we try to take the limit of this result here when n goes to infinity, we have this result. It doesn't know how to calculate. So there is this limitation, but we can still use up to a certain level. This next example is a simple example, and we want to convolve a signal x with a filter impulse response h using the z-transform. So we know that the convolution in time is equal to a multiplication in the z-domain, so we can make take the z-transform of both the signal and the filter impulse response, multiplying the z-domain, take the inverse z-transform, and we will have the result of the convolution of x with h. So if we take the z-transform of x, we have this polynomial here. The z-transform of h, we have this polynomial here. And we multiply in the z-domain, we have this polynomial here. We take the inverse of z-transform, that we've seen that the inverse of z-transform are the coefficients of this polynomial. So we have this as a result of y. To see if it's correct, the convolution in the time domain, if we use numpy and we convolve x with h, and we have the same result. And also remembering that the convolution is defined by this equation here, we can implement this equation using pure Python without using numpy, and we see that we get the same result. So with this simple example, we showed that the convolution in time corresponds to a multiplication in the z-domain. So we took the z-transform of the sequence x and the filter impulse response h, we multiply them in the z-domain, we take the inverse z-transform, which is just the coefficients of this polynomial, and we have the result, which is the same as convolving the two signals. And that's it for the z-transform. Let's move on.